Ever wondered how AI reads, writes, and understands human language? The answer lies in a revolutionary architecture that's reshaping the field of artificial intelligence, the transformer model. Today, we're diving deep into the technical heart of transformers, exploring how they process information, why they outperform older models, and what makes them the backbone of cutting-edge NLP systems. Let's get technical. For decades, recurrent neural networks, RNNs, and their variants like LSTMs dominated natural language processing. But they had a critical flaw: sequential processing. Each word had to be analyzed one at a time, creating bottlenecks for long-range dependencies and limiting scalability. Imagine trying to read a book where you could only process one sentence at a time. Inefficient, right? That's the challenge RNNs faced. Enter the transformer, a model designed to break free from these constraints. The transformer's breakthrough lies in its self-attention mechanism. Think of it as a neural network's ability to focus on different parts of a sentence simultaneously. Here's how it works. For every word in a sequence, the model calculates a set of queries, keys, and values. The attention score between a query and a key determines how much weight the model gives to the corresponding value. This allows the network to dynamically prioritize relevant information, whether it's a noun phrase, a verb, or a contextual clue. It's like giving the model a spotlight to highlight the most important parts of a sentence, regardless of their position. But wait, how does the transformer know the order of words? Unlike RNNs, which process data sequentially, transformers need a way to encode positional information. That's where positional encoding comes in. By adding sine and cosine functions of different frequencies to word embeddings, the model learns the relative positions of words. This mathematical trick allows the network to infer relationships between words based on their distance in the sequence, mimicking the sequential awareness of RNNs without the computational overhead. The transformer's architecture is built around two main components: the encoder and the decoder. The encoder processes input data, transforming it into a series of abstract representations. The decoder then uses these representations to generate output, such as translating a sentence or answering a question. Each of these components consists of multiple layers, with each layer containing a self-attention sublayer and a feed-forward neural network. This stacking of layers enables the model to capture increasingly complex patterns, from local syntax to global semantics. Transformers outperform traditional models in several key ways. First, their parallelizable structure allows for massive speedups during training. Second, self-attention enables the model to capture long-range dependencies, which is critical for tasks like machine translation or document summarization. Finally, the scalability of transformers has led to models like BERT, GPT, and T5, which achieve state-of-the-art results across a wide range of NLP tasks. But here's the kicker: the same principles apply beyond language. Transformers are now used in computer vision, speech recognition, and even protein folding predictions. So what's next for transformers? Researchers are already exploring variants like the axial transformer, which reduces computational costs, and the sparse transformer, which focuses attention on the most relevant parts of a sequence. The future is bright, but the core idea remains the same: a model that can dynamically weigh information, adapt to context, and scale to unprecedented sizes. If you're interested in the math behind self-attention or want to see how transformers are implemented in code, hit the subscribe button and check the description. Thanks for watching, stay curious, and keep pushing the boundaries of AI.